Today we're going to be talking about chemistry. Okay, some of our goals are going to be to define matter and elements, describe the interrelationships between protons, neutrons, and electrons, and describe different kinds of bonds. So what is chemistry? Chemistry is the study of matter. Another thing you want to look at when we're studying matter is biology. If you recall, biology is the study of life. And also something else you can relate to is physics. Physics is the study of how energy relates with matter. So what is matter? Matter is anything that has mass and takes up space. Can you think of anything that does not have matter? An example of something that does not have or have anything to do with matter would be ideas or even shadows. Another note to make is that you cannot create matter. You can only change the form of it. If you look at your periodic table, there are actually 92 naturally occurring elements. The rest of the elements that you maybe have heard of are actually made by humans. The thing that distinguishes one element from another is actually the number of protons. A compound is two or more different elements combined in a fixed ratio. In this example, you can actually see sodium chloride, which is NaCl. That is considered a compound. H2O, water, is considered a compound. And there are some essential elements that are essential for all or most living things. They are made up of what we call Ch2, carbon, hydrogen, oxygen, and nitrogen. There are a couple other trace elements that are required and essential for living beings, and those you mainly get from your food that you eat. If a plant has a nitrogen deficiency, it will usually not grow very well and even end up turning yellow. Iron deficiency is something that you see in a third world country somewhat, because in the United States they actually inject iodine into salt a lot of the time, and of course there's a lot of things that we eat that have salt, so we actually get a lot of iodine. But in other places, they can actually develop an iodine deficiency. That can lead to a goiter, which is pretty much this large mass growing in the thyroid gland of this individual. Each element is composed of atoms, and an atom's definition is the smallest unit of matter that still retains the properties of that element. Now, I don't know if you've ever seen an actual atom, okay, but there is a really good link that you can click on or copy and paste it in your own window. So you can go ahead and take a look and check out the atoms and the actual shadows that actually consist or make up the atoms. Next, we're going to start talking about subatomic particles, okay? So when we're talking about protons, to start off, protons are pp. Positive, okay? So protons are positive. That's how come I remember it, pp. So protons are positive and they live inside the nucleus, okay? There's going to be pretend there's like a fake little circle around here. That's going to be where the nucleus is, okay? So here's the protons, which are positive, the pink color. Then you also have neutrons. Now neutrons are neutral. They don't have a charge. They're right here, these brown little things right here, and they also live inside the nucleus, okay? One key thing to mention right here is that the number of protons never ever changes, okay? Because that's also equal to the atomic number of an element. So the number of protons will never change. However, the number of neutrons can change, and if they do change, they are basically making what's known as an isotope. So the number of electrons. Now, for a neutral atom, which is any of the ones that are found on the actual periodic table, and there of course are other forms of those elements, but for the case of just talking about neutral atoms right now, for neutral atoms, this number of protons is also equal to the number of electrons. So in this example we're looking at right here in front of us, we have 2 protons and then we'd have 2 electrons for this neutral atom right here. Also remember that these guys are measured in Daltons. So if you look at the periodic table under atomic mass, you'll actually see the grams in Daltons, but you have to remember that Daltons is equal to 1 gram as well. So you can actually go ahead and interchange those out pretty easily, okay? Now here's a periodic table. So we're going to be talking about valence electrons, which are the outermost electrons of an atom, in just a second. But for now, let's go ahead and look at the groups. So the groups are, if you're looking at these guys as columns going up and down, okay? These are called groups, or they're called families. And we're going to go ahead and number these 1, 2, and skip these, all the middle, right here to right here. You're going to skip them because these are your transitional metals, okay? But 1, 2, we're going to label this one 3, 4, 5, 6, 7, and 8. So basically, all of these in this column are in group 1, all of these in this column are in group 3, and so forth. What this group number is actually telling us is the number of valence electrons in the outermost electron shell of that atom, or of that element. So for example, helium, neon, and argon all are going to have 8 electrons floating around in their outermost electron shell. Whereas, let's say we're talking about boron. Boron only has 3 valence electrons in their outermost electron shell. So let's say we talked about those groups which are going up and down. So going across this way in rows, okay, these are going to be the energy levels. So you have 1 energy level, 2, 3, 4, 5, 6, and so forth. So let's say we're drawing, boron. If you're looking at this on the left-hand side first, this is going to show you how many energy levels you need to draw for that particular element. And then this one's going to tell you how many electrons are in the outermost shell. So let's say this is our nucleus. So then this is the one shell. And this one says it's going to be 2 shells. And I'm going to fill this in right here so we know this is the nucleus. It's not an energy shell. Okay, it's actually the nucleus where our protons and neutrons are. Okay, so this right here, remember, going down the rows, it tells us how many shells there are for that element. And we're drawing boron. So 2 shells, 1, 2, and then here's 3 valence electrons. So we're going to go ahead and draw 1, 2, and 3 electrons in our outermost valence electron shell. So one key thing to remember is that on energy level 1, only 2 electrons fit. Any energy level above that, like so 2, 3, 4, 5, you can actually have up to 8 electrons in those shells. That is called the octet rule. So, first things first, let's go ahead and talk about the atomic number. These are common things you're going to find in the periodic table. So the atomic number right here is also equal to the number of protons of an element. Once again, that will not change. And the number of protons, if it changes from one to the next, that's a whole different element you're talking about, okay? So atomic number, and remember, if it's a neutral element, then the atomic number, or the number of protons, will also equal the number of electrons. So the atomic weight is listed right here. This one is always going to be unrounded. So you're going to actually see 1.01. If somebody's talking about the atomic mass, then you can go ahead and round that number. So if this is the atomic mass we were talking about, then we'd go ahead and round that to a 1. Okay. And isotopes. Remember we mentioned this a little while back ago. So basically an isotope is an element that's going to have the same number of protons but a different number of neutrons. So a good example of this is carbon. Right here you see carbon 12. This one, the proton number is 6, but the actual atomic mass is 12. Here the proton number is 6 once again, but atomic mass of this one is actually 13 grams. And this last one, carbon 14, is proton number 6, or it has 6 protons in it. So it's the same element, but they have a different atomic mass, and here it is actually equal to 14. So protons plus neutrons equals your atomic mass. So as you can see, remember, the definition of an isotope is same number of protons, different number of neutrons. That's what's changed in the atomic mass of these three isotopes right here. A really good known example for carbon and these different isotopes is carbon dating, which helps us identify how old certain fossils are. But also remember, isotopes are actually very, very unstable. Okay, sometimes we're able to use isotopes to treat cancer because as they go ahead and travel through our system, they may go ahead. We can follow them according to the different isotope that we actually had that particular isotope attracted to a particular, let's say, cancer cell. And eventually it'll leave our system with no problem, okay? But these guys are actually very, very unstable. So, what is the definition of energy? Okay, the definition of energy is the capacity to cause change. When it actually does cause change, that is considered work. One example is potential energy. That is pretty much the energy that's stored within a system, but if released, can change into kinetic energy, but it's basically sustained and energy that can cause work, but is not at the moment. So a good example of potential energy I like to state is, let's say you're on a pinball machine. When you pull that lever back, you know, the one that actually swings out and punches the ball before it goes all crazy, when you actually pull that lever back or pull the spring back, that's actually, and you hold it there, that's actually potential energy built up within that spring. Because if you release it, it'll go ahead and change into movement of energy, which is kinetic energy. Different states of potential energy are called electron shells. So, remember how we stated earlier that in the first electron shell, only 2 electrons can fit? But any other shell after that can fit up to 8 electrons in their outermost valence shell. So, if you look right here in orbital or shell number 2, we have 1, 2, 3, 4, 5, 6, 7, 8. And then, of course, shell 3 would have to be filled next. So as you move up in shells, as the elements get bigger, each shell has to be filled before another one is actually developed. So all these are filled up. So there's 2, 8, and 8. And then this valence shell, which valence means the outermost shell, in this particular element of potassium, there's actually 1 valence electron. So this is the electron that's in the outermost ring. So valence electrons are electrons in the valence shell. Pretty simple, but it's going to be the electrons that are in the outermost ring. Okay, the maximum number of the maximum number of electrons in a shell are going to basically depend on how that particular element reacts with anything else. So if you go back to look at your periodic table, any of the elements that are in group 8, the ones that were in the far, far, far right-hand side of our periodic table, those actually have 8 electrons in their outermost shell or in their electron valence shell. What does that mean? That means that any elements on group 8 are going to be considered inert. Inert means they're unreactive. They don't want to respond or they don't react with any other element, really. All the other shells, like let's say group 1, group 2, group 3, group 4, all the way up to group 7, they don't have a full electron shell. So they don't have the full 8 electrons in their shell. So their reactivity is going to be a lot higher compared to our group 8s. Okay, basically everybody who does not have a full valence electron shell, they're trying to go ahead and exchange or grab onto other electrons by bonding with other elements. Based on electron configuration, which of these elements would exhibit chemical behavior most like that of oxygen? So to answer this question, you would have to refer back to your periodic table. And go ahead and take a second and think about which one of these would actually react very, very similarly with oxygen. Or not with oxygen, I mean like oxygen. So look and see. Remember, their group or families are very similar as far as their reactivity levels. So go ahead and go back to your periodic table and see which group, which is pretty much the columns, that oxygen is, and see if there's any others that are similar to that. Remember, because that tells us how many valence electrons there are in that particular element's drawing. Which drawing depicts the electron configuration of neon? So you can do this two ways. You can go ahead and look at the periodic table and see how many actual electrons there would be for neon, and then count every single one of these electrons. Or you can do the shortcut method, where you actually first look on the left-hand side of the periodic table and go ahead and look at the rows first so you can see how many valence shells there are, or how many orbital shells there are on the left-hand side. Then go ahead and look at the top part and find neon on the top of the periodic table and see which group number it falls into, because that'll also tell you how many valence electrons you should be able to count on the outermost valence shell. Okay. So let's start talking about chemical bonds. There's a covalent bond, which is the strongest of all the bonds, and it is formed by the sharing of a pair of valence electrons by two atoms. An ionic bond are basically metals that lose electrons, and nonmetals are the ones that gain electrons to have an octet full valence shell. A hydrogen bond, which is weaker than even these two, so it's like the strongest, second strongest, and then the hydrogen bond is next, is whenever you have hydrogen pretty much attaching to other compounds. So in this case of H2O, or water, remember that? We actually had water molecules that were attracted with between one another through hydrogen bonding. And the weakest of all the bonds is going to be van der Waals interactions. This is just the fleeting attractions of molecule to molecule. I like to think of this one as static electricity. Kind of like, let's say when you get a balloon and you rub it really, really fast against your hair and then kind of pull it off just a little bit, and you can actually see that static attractiveness from your hair to the balloon. That's kind of how I like to think of van der Waals interactions. They're very, very, very extremely weak. So talking about covalent bonds first. Remember, covalent bonds is basically the sharing of paired electrons between two atoms. So right here, we actually have nonpolar covalent bond example, because they're actually equally sharing the electrons going around both of the atoms equally. So both of these are considered nonpolar. They're equally going to share nice and evenly their outermost electrons. So, valence. The number of covalent bonds an atom can form equal to the number of unpaired electrons in the outermost shell. Remember earlier we were talking about valence electrons? So, right here would be a good time to go back to your periodic table. If we're asking what is the valence of hydrogen, okay, you're going to want to be able to look at the periodic table and look at the group numbers of each of these elements. So let's start with an example with oxygen, okay? Oxygen on your periodic table is under group 6. So that means oxygen has a valence of 6 electrons in the outermost shell. So 2 more are going to be needed to fulfill that 8 octet rule that we have. So therefore, oxygen would have a valence of 2. Nitrogen. If you look at nitrogen, it actually is in group 5 in your periodic table. So it actually has 5 valence electrons in the outermost shell. So it would need 3 more to fulfill that shell itself. So basically the number would be 3 for nitrogen. Which drawing depicts an atom with a valence of 2? So that basically means we need to find an atom that has 6 valence electrons in its outermost shell, because then that means it has a valence of 2. So I'll go ahead and let you all figure that one out. Compounds, unlike molecules, are 2 or more different atoms in a fixed ratio held together by covalent bonds. Okay, 2 or more different atoms in a fixed ratio. So right here we have 2 different atoms. Here's hydrogen, here's oxygen, and that is our water molecule right here. Okay, and now I just wanted to have you guys remember, water molecule 1 in itself has actually a covalent bond right here, and it is actually polar covalent here. Okay, remember, water molecules, bonds within themselves are actually hydrogen bonds, but one molecule by itself, or one compound of water by itself, is actually has a nonpolar covalent bond right here. Electronegtivity. It is the attraction of electrons in a covalent bond. So in this picture of actually the water molecule, you'll actually see, remember, polar covalent means unequal sharing of electrons within a compound. So right here we have the negative pull of oxygen, it's negative, and we also have the positive pulls of hydrogen on each side. So there's actually a stronger pull of shared electrons toward itself to this electronegative portion right here. Remember, the electrons are basically circling around each of these atoms, but they're going to be actually spending more time around the oxygen atom than the hydrogens, just because of the greater pull going this way. That is why it is considered a polar covalent. Nonpolar covalent means there would be equal sharing of electrons in a compound. So an example of a nonpolar covalent compound would be hydrogen paired up with hydrogen. You'll have the equal sharing of the electron pair around each of them. Ions and an ionic bond. So an ion is formed when an atom gains or loses an electron. Remember, ionic bonds are basically where one metal loses an electron and one gains it. So when that happens, you have ions form. Okay, you have an anion form. First of all, anion, I like to think about it like anabolic steroids. Remember, anabolic steroids are those big, heavy-duty muscle-building power builders. They build up muscle, right? So an ion, they're going to gain an electron. So in this example here, we actually see the chlorine atom is actually gaining this electron from this sodium atom. So this is going to be considered, at the end of the day, the anion. The cation, remember, cats like to tear things apart. So I have to think about it like this poor little sodium is getting torn apart and that electron is getting torn off of it. So now it is considered a cation. It lost an electron. Okay. Ionic compounds basically is when an ionic bond is formed when two atoms are so unequal in attraction for valence electrons that one atom strips an electron completely from the other. So one example we just looked at right now was the building up of sodium chloride, which is aka your table salt. Recap, remember, hydrogen bonds can be very, very weak and they're very brief, 1/1,000,000th of a second in between each one, because these water molecules are constantly moving very, very quickly. Okay. And remember, van der Waals interactions is the weakest of all the bonds and is when molecules or atoms in close proximity can be attracted by fleeting charge differences. So recap of everything we've covered in this lecture is we define matter and different elements. We describe the interrelationships between protons, neutrons, electrons. Don't forget we mentioned isotopes too. And we talked about all four of the different kinds of bonds.